All right, in section 12, we're going to be looking at exponential functions. We had just looked at logarithmic functions in section 11. It's pretty much a lot of the same things. This one, it actually looks a lot like the first lesson we ever looked at, the linear equations, but now exponential. And the reason being is because I'm going to show you what each variable stands for and how we can use them to solve problems. So, an exponential equation is of the form y equals ab to the x. So, what does each variable represent? Just like linear equations, y is still the dependent variable because it depends on what x is. But a and b are going to be different here. A is always the initial amount. All right, and I'm going to show you what that means with an example. B is the ratio. And then x, just like in linear equations, or pretty much all the equations we've been dealing with, is an independent variable. All right, so let's go ahead and look at an example here. Let's say we wanted to find the model, right? In other words, an equation of a substance, C27, that is 5 milligrams, so it's pretty tiny, but it doubles every hour. Like, how can we model that using an exponential equation? Well, y and x are always going to stay as just y and x. But what is a here? What is the initial amount? Initial amount, we're starting off with 5 milligrams. So in this case, a is going to be 5, right? That's where we're getting it from. Now b, the ratio. How do you find b? The way I figured b was 2, or if you want to go ahead and take a guess, the way we got b is equal to 2 is because it doubles every hour, right? If it was triples and b would be 3, quadruples would be 4, so on and so forth. So our equation, we just plug in those numbers and we get y equals 5 times 2 to the x. That is the exponential function modeling. Let me show you what that looks like if we were actually to apply it. Let's say after 5 hours, well, 5 hours, x is a dependent variable. We can plug in 5 into x, and that'll give us that after 5 hours, there is now 160 milligrams of C27. Now, this is a standard exponential equation, or the form, but there's one you might have seen before. We tend to use more for problems that are applied. And it's just another way to write exponential equations. I've heard people call it the PERT. I would just call it, the alternative way of writing an exponential equation. So same thing, y is still the dependent variable. It's going to depend on r and t now. But here, p is just another way of writing a, which is still the initial amount. E, if you remember from last lesson, right here, e is not a variable. If you remember, just like pi, e is an irrational number. And if you remember, it was something equal to something like 3.71, and then I forgot the rest, 828, something like that. But it keeps going on forever. R is what we call the continuous rates, and then T is for time. And again, let's go ahead and look at an example. I'm going to erase things here just so they don't get in our way. All right, so the example. In 1950, so back in the day, the population of a city was 10,000. And then 20 years later, the population was found to be 20,000. So in 20 years, it doubled. We need to find the exponential function that models the population y after t years. So how are we going to do this? Well, first things first, we need to identify what everything is, right? We're going to use this equation, but we need to identify what everything is. In this case, the dependent variable here is the the dependent variable here is going to be 20,000. How do I know it's going to be 20,000? The reason it's 20,000 is because they're already telling us that after 20 years, population was now 20,000, meaning Y was now 20,000 when T was 20. The initial amount, the stated population in 1950 was 10,000. So we're going to go ahead and plug those in. 20,000 after 20 years when we started with 10,000 and after 20 years passed. Now R, we don't know R. R is the rate. That's what, not we're trying to solve, but you know what, we're trying to model. And in this case, we probably will solve for it. E, we don't have to solve for it because it's already a number. So just like any other equation, we solve it by isolating the variable. So in this case, we'll start off by dividing both sides by 10,000. We'll get that 2 is equal to e to the power of 20 times r. Now, if you remember, the way to get rid of this e, or to simplify this, is to apply the logarithmic function to both sides. So if we apply ln to both sides, ln and e will now cancel. We'll be left with ln2 is equal to 20r. Last thing to do is to divide both sides by 20. So the 20s can cancel out. And we get that r is approximately 0.0347. So up here the question asked, find the exponential function that models the population y after t years. That is already here, right? We're going to use PERT. It's pretty self-explanatory. I would say, you know, if we wanted the actual equation for this scenario, it'd be y equals 10,000 e. And now that we have r, it's 0.0347 t. That is the equation that they're asking for. So these were two problems. I gave you one here and one last slide. That's pretty much it for our exponential functions. Like I've said a bunch now. In your packets, there are more problems you can practice with, or even look up some online, and we're always here for you to ask.